So in the last video, at least where we ended off, we talked about arc length and how essentially arc length is equal to the integral from a to b of dx dt squared plus dy dt squared, and then the square root of all of that. And then this is being integrated with respect to dt. And this is assuming that your function, right? So you can imagine that this is like a particle, right? This is like a particle traveling along a path. You can assume that, well, this is represented by something called a vector valued function. So r of t, usually denoted with arrow on top, it's going to be equal to some function of x of t, comma, y of t. And so this is just like the parametric equation that's used to model out the position of the particle at different times. So in this case, this would be one position, right? You would have a vector pointing to the next position of the particle, that maybe after another bit of time, the particle is now at this spot right over here. And so the vector value function is just a fancy way of just modeling the position of the particle, in this case, after some period of time. And so arc length is just, you're just spamming the Pythagorean theorem to find out the length of this path, right? So the length of this path that the particle has traveled, okay? But I'm here to give you another perspective on this arc length formula. So first of all, let's consider what r prime of t is equal to, right? What is r prime of t equal to? Well, we said how if you differentiate position, right? So if r of t represents the particle's position at some time period, then if you differentiate this with respect to time, you're going to get your velocity function. So this vector valued function. All right, I had to delete some stuff because the storage was full. But r prime of t, that's just going to give us the velocity. All right. So in this case, this would be a function. R prime of t would just be composed of x prime of t and y prime of t. Okay. So we can think about what is velocity really saying, right? What is r prime of t really saying? You're basically finding out the rate of change of your position with respect to time. So this is dr of t, comma dt, or sorry, not comma dt, over dt. All right. So the rate of change of your position over time gives you velocity. In physics, maybe like just a simpler version of this formula would be that your velocity is just going to be equal to your displacement over time, right? You've probably seen this in physics before. Well, these are just the exact same thing, right? dr over dt. Well, what is dt? That's just a tiny change in time, right? dr, well, that's just going to be a tiny change in your position. And a change in position is just a displacement, right? If I go from one place to another place, there's going to be some displacement associated with my change in position. And so dr just represents change in position. And so this has to be velocity, okay? So that's another way that you can think about it. When in doubt, a lot of these concepts relate back into physics, so you can use your prior knowledge there to help you out, okay? Now, this is pretty interesting. I want to do something with the magnitude of the velocity vector, okay? Now, what do I mean by magnitude? So imagine that I have a velocity vector. This is my velocity vector. I'll just call this v. And let's say that this points to the point 3, 4. So my velocity vector is going to be pointing at 3, 4. What do you think the magnitude of the velocity vector is? So calculate the magnitude of this vector and tell me what it represents. All right, so just kind of predict what it represents. Well, this is just a Pythagorean theorem problem, and this is just a 3, 4, 5 right triangle. And so the magnitude of this velocity vector is equal to 5 units. And the magnitude of the velocity vector represents speed. Think about it. Speed is a scalar quantity. So there's a magnitude and there's no direction. Velocity is the vector quantity, right? It has a magnitude and a direction. So you would usually write out a vector if you're representing the velocity vector at some specific point. All right. But if I take the magnitude of this velocity vector, that's just going to give me my speed, okay? So I'm just going to write this down. The magnitude of my velocity vector, which you can think about it as r prime of t, right? R prime of t is the same thing as the velocity vector function, right? So absolute value of r prime of t is going to be equal to speed, okay? So at any time period that I'm looking at any t value I'm looking at, well, the absolute value of that vector that I get is going to represent the speed, okay? Now let me just make this notation simpler, actually. So instead of dr over dt, or sorry, dr of t over dt, this is the same thing as if I just put dr over dt, okay? So I'm just going to make everything simple, all right? So think about arc length, all right? So we're going to derive the arc length formula, but we're going to look at it from another perspective. So think about what happens when I move from one position to another position. So now we're looking at the position function, r of t, and what happens when I move from one place to another place. So let's say this is r of t, and then this next point would be r of t plus delta t, right? So it looks like that between these 2 points right over here, there's some change in position, right? There's change in position within these 2 points. And so this can be represented by some kind of vector, right? Now, if I wanted to find the arc length, well then, notice how if I wanted to find the arc length, aka the length of this vector, I would just have to take the magnitude of it. Since the magnitude of dr is equal to a tiny change in my arc length, well, if I sum up all these tiny drs along my curve, well then, I'm just going to get my arc length. So I can essentially say that the integral of the magnitude of dr along my curve, so from A to B, that's going to give me my arc length. Now what's dr equal to? We want to do this with respect to time. So how can I introduce time into this integral? And the answer is, well, you got to use differentials. So you might remember this once again from calculus, but differentials, it looks like you're multiplying both sides by dt. It's really weird. So I can say that dr is equal to r prime of t dt. Okay, so it's like we multiply both sides by dt. This isn't like a rigorous thing, and if you want me to make a video on differentials, feel free to comment below, but yep, this is the differential for dr, and then if I take the magnitude of this, I take the magnitude of dr, well then I would have to make this, in order to make this equal to each other, I would just have to take the magnitude of my velocity vector, right? Because dt, that's just a tiny change in time, and in r prime of t, that gives me some kind of vector quantity. And so in order to make this scalar quantity equal to a scalar quantity, I have to take the magnitude on both sides to make them equal. And well, guess what? I'm able to substitute this in for dr. And so this is another equation for arc length that you might see. This is another equation that you might see. All right. Now, you might say, well, Ryan, why is this arc length formula equal to the arc length formula that we saw before? Well, if I want to take the absolute value of a vector, right, then I'm just going to have to use the Pythagorean theorem on its components. So once again, like if I'm trying to find out the absolute value of this vector v, well, then I'm just going to square the component. So I'm just going to, if this was, for example, x of t, and this was like y of t, for example, in order to find out the magnitude of the vector, I would have to do x of t squared plus y of t squared, and I would have to square root that. Well, look at what we have here, right? This right over here is my velocity vector, r prime of t. And we say how my velocity vector has components of, so our velocity vector, r prime of t. You can see how if I want to differentiate a vector valued function, that's just going to be equal to the derivative of its individual components. So if my original position vectors were x of t, comma y of t, well then if I differentiate the actual vector valued function itself, aka dr dt, well then it's just going to be the derivative of its components, okay? So the derivative of a vector valued function is equal to the derivative of its components. And so if I want to find out the magnitude of all of this, well, then we know how to find out the magnitude for components of a vector. It's just going to be this component squared, dx dt squared, plus this component squared, dy dt squared, and then we square root all of this. Okay? So one interpretation of arc length is that, well, it's just going to be Pythagorean theorem, and you're just spamming it all over this arc length, or all over this from a to b, this interval. But another interpretation of arc length is that, well, r prime of t, the absolute value of r prime of t, that's just going to give you your speed. So if you integrate speed with respect to time, well then, and you sum it all up from a to b, that's going to give you your total distance, which you can think about as essentially the arc length. So just a quick practice problem. Find me the arc length for this function from t starting from 0 to all the way up to 6. Okay, so I want you to find out the arc length in this interval right over here. Okay, let's start. So to find arc length, remember what we got to do. We got to differentiate this. R prime of t, what is that going to be equal to? That's going to be equal to 5, 12. So that's our velocity vector. And then if I take the absolute value of this, well then, what's the absolute value of this vector right over here? Well, the magnitude of this vector right over here, so the x component is 5 and the y component is 12. So the magnitude of this, that's just going to be equal to 13. And so we said how the integral from, in this case, 0 to 6 of our magnitude of the velocity vector function, or yeah, the velocity vector valued function with respect to time is going to give us the arc length. All right. And once again, just to make things simpler, we said how arc length basically represents the distance traveled, right? If I go from one point to another point and I find out the arc length of this, well, that gives me the total distance that's traveled, right? So this right over here represents the displacement. It's a vector quantity that represents kind of, you can think about it as like the net distance from one place to another, like the quickest path to get to one point to another. But the total distance traveled, that's a scalar quantity. And so this arc length right over here is going to represent the total distance traveled. And I'm going to call this new quantity S. So the distance traveled, I'll just call that S, okay? And so S is going to be equal to the integral from 0 to 6 of 13. This is the same thing as 13t evaluated from 0 to 6. Well, if I plug in 0 here, that's just going to be 0. So all I have to do is just find 13 times 6, and I'm too lazy, so I'm just going to use my calculator, and I get 78. Okay, so that is the total distance that's traveled. Now, if this practice problem was asking me to find out, instead of from 0 to 6, right, find a way to relate time to arc length, so we just wanted to establish a relationship between t and s, and we didn't really want to evaluate it between an interval, well then, this would just be my answer. We get that the arc length is just going to be equal to 13 times the time, right? So this is just a relationship between arc length and time without, along a certain interval. It's just the indefinite integral, okay? Now, of course, there might be like a plus c here, but let's just keep things simple, and let's just say that whatever constant that we have is equal to 0, okay? Let's just keep things simple. Since we established a relationship between time and s, or distance traveled, or arc length, we can divide both sides by 13. So I get that t is going to be equal to arc length, or I'm gonna start calling it distance from now on. So it's going to be equal to the distance divided by 13. And notice how we have our original vector valued function right over here, and it's expressed in terms of t. What if we expressed the same particle, right, the same position function, but instead in terms of s? So everywhere I see a t, I'm just going to substitute it for s. So instead of r being a function of t, it's going to be r as a function of our distance traveled. So based on the distance traveled, what is going to be our position? So now we're kind of reinterpreting the idea of our function, right? Originally, r of t is basically saying, given a time, give me the position. But r of s is saying, given the distance traveled, find me the specific position the particle is in, okay? So this is going to be 5 divided by 13, 5s divided by 13, comma, 12s divided by 13. right? All I did was I just replaced the t with s over 13, okay? Now, believe it or not, we actually did something pretty special, and we did something called reparameterization. So as simple as simple as it looks like, you know, we're just replacing one variable, in this case t, in terms of another variable. So our position now depends on that other variable that we're looking at. But reparameterization also has some other effects. And so I have Desmos pulled up here, and tell me what you notice. So our original function looks like this. It's in the orange. And our new function, after we reparameterize it, AFT, BFT, well then it's represented by this little blue line right over here. Notice how it still traces out the same curve. Like if I let t range from a very big value, at the end of the day, it still traces out the same curve, right? So something important to know about reparameterization is that it still traces out the same curve. And the reason why it traces out the same curve is because we're replacing both our x component and our y component with the same thing. And so overall, the position of our particle over whatever variable we're looking at, it's still going to trace out the same path. But notice how the speeds are going to be different, right? So let's say, notice how for the original function, right? So this w right over here, it represents like the position of a particle at a specific point for our original functions. So they're represented by time. And notice how as I change w, right, the particle is very fast, right? So if I express the position in terms of time, the rate of change of the position of this particle is going to be extremely quickly. It's going to go extremely quick. However, if I reparameterize the function in terms of the distance that it travels, well, notice how it goes way slower, right? And so reparameterization, you can get the same curve, but chances are that the speed is going to be altered. The speed of your curve, the speed at which it's traced out, is going to be altered a bit. And in this case, when we're expressing the position in terms of our arc length, well, it's going to be extremely, extremely slow. Like think about this mathematically, right? If t is equal to 1, then in order to make this equation equal to each other, our arc length has to be equal to 13 to create the same effect, right? And so this is the thing about reparameterization. It changes the speed, and because we're representing things in terms of the distance that we traveled, well, the distance is going to change way slower than if we were looking at how the position changes with respect to time. So think about it like this, right? Imagine if t is equal to 0, right? If t is equal to 0, then we are going to get r of 0, which is equal to 0. And notice how that's the same thing for r of s, right? If r of s is equal to 0, or if s is equal to 0, right? If we haven't traveled any distance at all, then our position is of course going to be equal to 0. And so this constant right over here that I've kind of been neglecting before, that represents a sort of starting point. The constant represents our starting point, right? Starting point. If let's say the integral of 13 dt, let's say if we said that was equal to 13t plus, let's say 13, and then I subtracted 13 from both sides, so I get s minus 13 is equal to 13t, and then I'll divide both sides by 13, right? And then notice how when I plug in 0 in for s, this is going to take on the same value as when t is equal to -1. And so if I added an arbitrary constant right over here, then when we have r of 0, where this is r of s, right? If we're expressing our position in terms of the arc length, then if we added this constant right over here, our r of 0 value is going to be equal to r of 1 if we parameterize this using time. So adding a constant, that all that does is it changes your initial position. If I let our original function be equal to -1, we get 5, -12. And notice how that's equal to if our function in terms of the arc length is equal to 0, right? Now you might ask me, all right, Ryan, we parameterize R of t in terms of the arc length. Why is that even important in the first place? Well, now we're going to introduce the chain rule, and we're actually going to see something called the unit tangent pop up. And we're actually going to see why when we reparameterize by arc length, that actually removes something called the speed dependence, okay? So take a look. If I'm trying to find out the rate of change of our position with respect to the distance traveled, which is s, that's just going to be dr over ds, right? And using the chain rule, we can say that dr over ds is equal to dr over dt. So how does r change with respect to time? Multiplied by how time changes with respect to that s variable that we introduced, right? So to find dr ds, right, remember how we initially established a relationship between r and t, and we multiply that by the new relationship that we established with t and s, right, from the integral that we did with the practice problem. All right. Hopefully, you still remember that from calculus. And let's actually do something pretty cool. dt over ds. dt over ds. Let me just flip that fraction real quick. All right, I know that's not really a fraction, but let me just flip it. So instead of dt over ds, I'm just going to write it as 1 over ds over dt. So I know that dr over ds is going to be equal to dr over dt, which, I mean, we know this is the velocity, right? So dr over dt, that's just going to be the velocity, r prime of t, right? And this is going to be divided by ds over dt. Now, if you recognize this from physics, ds over dt, you might recall that ds over dt is just going to be equal to the speed, right? Recall that dr over dt, that's the rate of change of our displacement, and displacement is a vector quantity. So that explains kind of velocity as a vector quantity. But recall that speed is a scalar quantity and distance is also a scalar quantity. All right, so ds dt represents our speed, which we can interpret as the magnitude of our velocity, right? We said how our speed is the magnitude of our velocity. Another way to interpret why ds over dt is equal to the magnitude of r prime of t is because, remember the arc length formula. We said how the arc length formula, or this is essentially our distance, right? The arc length, it represents our distance. Well, the distance is just going to be the integral of ds over dt with respect to time, right? Which is the same thing as the integral of the magnitude of r prime of t with respect to time, right? If you like looking at calculus from an informal way, then the dt's cancel out and the integral of ds is just going to be s, right? But if you want to look at it in like a more formal way, then, well, this is just going to be like the fundamental theorem of calculus, right? If you're integrating ds over dt with respect to time, well, then that's just going to give you your net change in distance. And so this right over here, this ds over dt, we can replace it with the magnitude. We can replace this with the magnitude of r prime of t. So because we're dividing a vector by its magnitude, this overall vector right over here, this dr over ds, is going to be normalized with unit length, okay? So this vector is going to be normalized, and it's going to have a unit length of 1, okay? So that explains why when we reparameterize our r function in terms of this new variable s, right, the distance traveled, well, because of this proof, well, we see how dr over ds is normalized, and the way to interpret this is that it removes the speed dependence. And so this actually has a name. This dr over ds, this is something called the unit tangent vector. And this is represented by this big T, and usually, it's a function, you write it as a function of time, and maybe there's like a hat on top of it, but because this is a unit vector, but this is something called the unit tangent. dr over ds is the unit tangent vector. Why is this the unit tangent vector? Well, think about it, right? R prime of t, this gives us the direction of the tangent line, right? Because if you have a curve and it's changing with respect to time, well then r prime of t tells us our velocity, which is essentially tangent, right? Which is tangent to this position function. That's literally the definition of the velocity vector, right? It's dr over dt. But because we normalize these vectors, well then it's going to become unit length. So you can think about it as just velocity vectors, except all of them are just going to be scaled down to a unit length of 1. The magnitude of these vectors are always going to be 1. Of course, they're pointing at different directions, so it's going to be different vectors all around, but the point is that the magnitude of these velocity vectors are just going to be a normal length now, right? So the main point that I want y'all to take away here is that dr over ds represents something called the unit tangent vector. And it's still going to point in the direction of, where the derivative would normally be for a position function, right? Because at the end of the day, when you reparameterize a function, it's still going to give you the same curve. But the difference is that because we parameterize it with respect to the distance traveled, everything is going to be of unit length. All right, so the velocity vectors are going to be a unit length, hence why it's called a unit tangent. So this is just a little review of what we've done, because this can seem a little overwhelming, but when we look at arc length, that's literally just the same thing as looking at a certain distance that we traveled. And we saw the proof for the unit tangent vector, as we saw that's equal to our velocity divided by the magnitude of the velocity, aka the speed. And so you can think about this magnitude of the velocity here as a normalizing of our velocity vector function. So that's why we get a unit vector as the result. And because if we parameterize a function, we also know that, or if we reparameterize a function, a vector valued function, we know that if this is, let's say r of t, if I reparameterize this function in terms of s, so if I did r of s, if I graphed out r of s, it would look the exact same. And so this unit tangent vector can still be applied to my original function of r of t. It can still, the unit vectors, or sorry, the unit tangents would still be completely accurate for my original function as well. All right. And in case kind of one interpretation of the unit tangent wasn't enough, let me give you another kind of interpretation. Okay, so another way that I can get this unit tangent right over here. And we're still going to continue using the chain rule, but in this case, it's going to be a little bit different. So instead of looking at dr over ds, I'm going to look at dr over dt. And I know that's equal to velocity, right? Now velocity, what do we know velocity is made out of? We can think about velocity as essentially having a speed, and then it also has a direction, right? Hence why it's a vector quantity. Or sorry, not speed plus direction. I'm going to put it as speed times direction. All right, this is going to start making sense. So dr over dt, we can use the chain rule so that we get dr over ds multiplied by ds over dt, right? This is just an application of the chain rule. And we know that ds over dt gives us essentially the speed, right? It's the magnitude of the velocity vector. And if we have the magnitude of the velocity vector, the only part that we're missing is the direction part. And so we know that dr over ds has to represent the direction of our velocity vector. So this has to represent the direction of the velocity vector. And because speed is just a magnitude of velocity, then this right over here has to have a magnitude of 1, meaning that this represents the unit tangent. Okay. Now let's talk about circular motion. And circular motion it's exactly what it sounds like, right? You're just moving along in a circle. And we're going to try and find out specific facts that you might have heard in physics, but you don't really know why it's true. And I'm going to greatly oversimplify this problem because I'm going to use the planets. Okay, so this right over here is the sun, and this right over here is like Earth. Now, you might have heard that planets actually orbit the sun in like an ellipse shape. So I'm greatly simplifying this problem by making this a circle, okay? Now, one thing you might have remembered is that when you're moving in a circular path, the first thing to know is that, well, the sun is in the middle and the Earth is right here. The sun is going to exhibit a strong force of gravity, right, to the Earth. because the sun is so large, the force of gravity that the sun has is very, very big. So it's going to attract the Earth towards its location, meaning that the Earth is actually going to be accelerating towards the sun. So whatever the direction of the force is, that's also going to be the same direction at which the Earth is accelerating, because we know that force is equal to mass times acceleration. Force is a vector quantity, so it has a specific direction. Mass is a scalar quantity, and acceleration is a vector quantity. So whichever direction force is pointing, acceleration also has to be pointing in the same direction. Okay? So we're going to be pointing towards the middle. All right, so wherever is like the middle of the circle, we're going to be pointing towards that. Now, what about the velocity? What do you remember from physics? It turns out that when you're examining the velocity of this object, it's actually going to be tangent. All right, so the velocity vector right over here, that's going to be tangent to the path it's kind of traveling. And finally, the last thing that you might have noticed is that, well, the acceleration vector and the velocity vector, they are 90 degrees to each other, okay? So they're going to be perpendicular. The way to intuitively understand how this centripetal acceleration and this centripetal force, that's what we call it, right? The way to understand why this works is, imagine if you just have a particle and it just wants to move straight, because the object in motion, it wants to stay in motion. So imagine if I'm at this point, right? And my velocity is right over here. It's tangent to this circle. And so if there wasn't any attraction to the sun, I would just keep moving in a straight line, right? However, the sun is pulling me towards the center. So my path is actually going to curve a little bit, right? So I'm actually going to curve a little bit. Imagine if I'm at this point, right? I want to be tangent. I want to get out of this orbit of the sun, but this sun is pulling me towards it. And so I'm going to curve a little bit, right? I'm trying to travel straight, but I'm being pulled towards the center. So I'm going to form a circular shape as a result. Now let's get into more of the math bits of circular motion. So this is how circular motion is generally defined. So you have r cosine of, and in this w, you usually see it with a fancy kind of w, which is omega. So r cosine omega t, comma r sine of omega t. Okay? Now let's take a look at this. Let's say that we let omega be equal to 1. Notice how when omega is positive, right? So when it's positive 1, you're traveling counterclockwise. When omega is negative, you travel clockwise. So you travel clockwise. The magnitude of this also matters. If omega is extremely large, you travel around the circle very quickly. If omega is very small, I'll just put 0.5 here, you travel around the circle extremely slowly. Okay? The reason why when I put it to 0.1, it showed half the circle is because I forgot to make t make a big range. Okay, so there we go. You can see how slowly it's traveling when the absolute value of omega is very, very small. Okay, so here's just a quick guide. Greater than 1, counterclockwise. Less than 1, that's going to be clockwise. And the absolute value determines the speed. Now imagine if, once again, this is a vector valued function. So our position is going to be determined based on like a vector that's pointing to our position. So like our position, right, is represented by a vector that points to that specific location that we're on. All right. Now notice how whenever we're traveling around the circle, we make an angle with the x-axis. And so this would be the angle that's created with this red vector. This angle would be the angle that's created with this white vector. And so we can actually define omega as being the rate at which this angle changes with respect to time. Think about it. If omega is really, really big, we said how a large value of omega would make you travel around the circle quicker. So the angle would be changing at a much quicker rate with respect to time. But if omega is really, really small, then we're not going to be moving around the circle as fast. So the rate of change of the angle with respect to time, that's going to be a really, really small value. In calculus, I mean, we almost always use radians. And for time, let's just say that we use seconds. So the units for omega is going to be radians per second. Okay? Now let's get into the differentiation. Okay. So let's differentiate this to find out the velocity. So we know that the velocity, aka r prime of t, is going to be equal to, and then now we just have to use our derivative rules. So this is going to be equal to, well, the derivative of sine is going to be, or sorry, the derivative of cosine is going to be negative sine. And we are going to have this w omega t, right? And it's going to be multiplied by omega because we're differentiating with respect to time. So we have to use the chain rule. And so this is going to give you omega times r sine of wt, omega t. So here we have it, right? I differentiated this r sine of omega t, and I got, well, derivative of sine is cosine, and we multiply by omega because of the chain rule. So there we have it. Now let's prove that the velocity vector and the position vector are perpendicular to each other. So that would be like the velocity vector would be in this direction, and then your position vector would be in this direction. So they're perpendicular. Well, I know that two vectors are perpendicular if the dot product of them is equal to 0. So if I take r of t dot r prime of t, if the dot product between them is equal to 0, then I know that our vector, our position vector, has to be perpendicular to our velocity vector. Okay? And if you actually do take the dot product, it's not hard to see like why they're equal, because this is just going to be negative omega r squared sine omega t cosine omega t, and you get the same thing here except it's positive. And so it would add up to 0, and so the velocity vector is going to be perpendicular to the position. Differentiating this, once again, we get these two results. Okay, and this represents the acceleration vector now. Let's factor out omega squared from this. So I'm going to get negative omega squared, and then notice how the rest of this is just our original r of t. And so we can rewrite the acceleration vector as just being negative omega squared multiplied by r of t. Due to this negative sign here, we know that this acceleration vector is going to point opposite to the position vector. And so hence why the acceleration vector, to visualize this, points opposite to the position vector. Final thing I want to talk about is the speed. So we saw how speed is just going to be the magnitude of this velocity vector that I have here. So it's going to be the magnitude of r prime of t. So take a second to compute the magnitude of this, and let's check our answer after we're done. So we know that in order to find the magnitude of this vector, it's just going to be this component squared plus this component squared, and then we take the square root of it. Now it turns out that after you're done with all of that, you're just going to get that the magnitude is equal to r, the radius, times omega. So what this basically means is that the speed, the magnitude of this speed is going to be constant. It's only going to depend on the radius, and omega actually stands for something called the angular speed, right? It's the rate at which the angle is changing. So sometimes you might also hear it called the angular speed. But the point is that the magnitude of this velocity vector is going to be constant, okay? So that's another important idea to know. And finally, we are on our last topic, the cycloid. All right, this is our last topic before the video ends. So let's actually understand what the cycloid is. So in the blue right over here, this is the point that we're going to focus on. And this is a point on a rolling wheel. So as the wheel rolls forward, right, the point is going to go up because it's going up the wheel, but it's also going to move forward because the wheel is moving forward. And we want to somehow model the position of this point. as it's rolling. And we also want to find out what happens at the bottom of this, right? Is there any way that we can explain why this is making these like hilly bumps, and then all of a sudden, like it looks like there's some kind of like asymptote kind of behavior here? I'm not exactly sure, but we're gonna find it out. Now, the first thing we have to do is we have to derive the equation of a cycloid. So how do we get the equation of a cycloid? So it's gonna have some x component and it's gonna have some y component, and we're gonna figure this one out. Okay, so I've kind of labeled this out. So we want to find out OP, right? We want to find out this vector OP and how we can model this. Well, then that's just going to be equal to OB, which is the vector from the origin to kind of the bottom of this circle, right? The point where the circle is touching the ground, plus the vector from BD. So the vector from the ground all the way up to the center of the circle, plus the vector from DP, which is the vector from the center of the circle to the actual point that we're going to be focusing on. Well, what's vector OB equal to? So they're all going to be split up into the components, that's for sure. So it's going to be some component plus this component vector plus this vector that has two components, right? Well, the simplest one is going to be the vector that's going from B to D. Vector BD has no x component, right? It's only pointing up. And the height of this is going to be equal to the radius of this circle. Okay. What about vector OB? Well, the distance that this circle travels is going to be equal to the arc length, right? Because think about it, right? As the wheel rolls across the ground, assuming that it's perfectly flat, right? The distance that it travels is just going to be equal to the arc length, right? So if the point, let's say if we have like a wheel here, right? And let's say this is our original point. And then let's say the wheel rolls right over here. Well, then the distance right over here is going to be same as the distance of the arc length that it travels, which is this distance right over here, right? It had to have rolled that much in order for the point to even get up here in the first place. And the formula for arc length, well, that's just going to be r theta, right? R times the angle that it rolled. And it's not going to have any y component because, well, it's OB, right? It's staying on the ground. The final part, DP, we're going to have to use some trigonometry. Now let's make our lives a little easier. Okay, so I've kind of enlarged this diagram, put it on another coordinate plane, and we see that this right over here is the angle at which the cycloid has traveled. All right, so the line from the center of the circle to your point, and then a line from the center of the circle all the way down to the x-axis, this gives you the angle that's traveled. And one way to think about it is that when you're starting on the cycloid, the angle is 0. So if you draw a straight line from the center of the wheel to the x-axis, that's going to form an angle of 0. And then as the wheel rotates, right, as the point goes here, this angle starts getting larger and larger. Okay? Now we can actually use some trigonometry to find out the point. So I'm actually going to shrink down this theta symbol because it's a little big. And I'm going to draw a right triangle. Notice how this right over here is just the radius of a circle. And I can actually find point P just from this using trigonometry. What's this side going to be equal to? What is this side going to be equal to? Well, I know that cosine of this angle is going to be this adjacent side, which I'm just going to call y. So cosine of the angle is going to be equal to y over the hypotenuse, which in this case is radius. So y is going to be equal to r cosine of theta. However, because we're going downwards in the y direction, I'll put a negative sign here. What about this x part, right? What is this x part equal to? Well, then you might have guessed we're going to use sine. So we know that sine of this angle is going to be equal to the x over r, right? If we multiply both sides by r, we get that r sine of theta is equal to x. However, once again, we're going in the left right? So that means that we have to have a negative here. So the coordinates of the point right over here can be represented by negative r sine of theta, comma, negative r cosine of theta. So if we go back to our parametric equations right over here, we know that this x component is negative r sine of theta, and then this one is negative r cosine of theta. Okay? And so let's add everything together. So r theta, so this is going to be r, and then if I factor out this r right over here, it's going to be theta minus sine theta. That's the x component of the cycloid. And then the y component of this cycloid is going to be r minus r cosine theta. So this is going to be r and then 1 minus cosine theta. And that's the equation for the cycloid. And assuming that the radius is 1, so if the radius is equal to 1, then you just have theta minus sine theta, comma 1 minus cosine of theta, which is what we see in this right over here. Sometimes, you might see it written with time. Sometimes you might see it written with theta because that's the angle. And, up here I wrote it as r of t, but, it's the same thing, right? R of theta, right? It's a function of this angle. And that's just going to be equal to everything that I have down here. It turns out that we can also apply circular motion formulas to help us derive the equation for a cycloid. So this is another way of doing it. So here's the given information. So normally when you have like a rotate or circular motion, normally you would just consider the point's position around the circle itself. But now the circle is actually moving. So you have to factor in rotational motion and the motion of the wheel itself that's like actually moving. So like you can think about it as the position is essentially kind of two parts. It's broken into two parts, right? The position depends on both the rotation that it undergoes, right? Both the rotation that it undergoes and the actual movement of the wheel as it goes forward. So I know that arc length, which is basically just s, right? It's denoted with s. That's equal to r, the radius, times the angle, theta. Well, if I differentiate both sides, I get the differential. So I get ds is equal to r times d theta. So depending on the radius and like a tiny change in my angle, that's going to cause a tiny change in my arc length, right? ds, right over there. We can substitute d theta, right? If I multiply quote unquote, both sides by dt, so I get that omega dt is going to be equal to d theta, okay? And then if I quote unquote divide both sides by dt, I get that ds over dt, which is the speed, which is essentially the speed of, how fast is the center moving. Well, that's just going to be equal to the radius multiplied by omega. And notice how that's the same result as when we differentiated, this vector valued function, and then we found the magnitude of it, we have the same result. Now, why does this make sense? Well, we know that this angular speed, this omega basically just controls how fast you're spinning around the wheel, and the radius also affects how fast you're spinning around the wheel. Think about it. This is when r is equal to 3. Now take a look at when r is equal to 10. Take a look at when r is equal to 10. Like, because the radius is just so big, it's going to move way faster, right? Because the radius is so big, completing one cycle, you're going to have way more arc length in the circle, and so over time, you're going to travel way more, right? So you can think about this r right over here as sort of like a scaling factor for both the x and y coordinate. The bigger the r, the further the point is going to travel over a certain period of time. So we're given the speed at which this wheel is moving, and we want to somehow convert this back into a position kind of function. Well, what we can do is we can integrate both sides with respect to time. And so we get that our arc length is going to be equal to, that's just going to be equal to our radius multiplied by omega multiplied by the time. So now that we have the speed of the wheel in the x direction, so based on how much time has passed, right, this is going to give us our change in position because the arc length is going to be equal to like the position that we traveled as seen in the other proof. So we know that the center in the x direction, well, it's going to have a value of the radius times omega times time, right? Relative to the starting point. So based on some time period, our new position is going to be whatever this value is. And our y value, well, what's the y value of this center? The y value of the center of the circle stays constant, right? The center of this wheel is constant. And so this is just going to be r. So as you can see, what I've kind of done up here is I modeled how the center of our cycloid, how does it change over time? And we saw how the y value stays constant at, just our radius. And in our x value, it changes according to this, based off of just integrating the speed of the wheel in the x direction. Because we know that arc length is going to be equal to how much we traveled in the x direction. Okay? Now, if I'm at the center, well, that's not really the most accurate way. That's not describing the position of a point on the wheel, right? And so to describe the position of a point on the wheel, well, I'm going to introduce another vectored valued function. So this vectored valued function up top represents how is the center moving over time. Well, the vectored valued function that I have below, this is going to model the position of the point relative to the center. So if I have my center here and I have this point P relative to the center, right, we're going to use our same trigonometry things before. And you might remember that in the x direction, we had negative r sine of, in this case, this is going to be omega t. And then in the y direction, we're going to have negative r cosine of omega t. So instead of theta, we're going to have omega t because we know that we're dealing with circular motion. Okay. And so to find out the position of the actual point itself, I can just add these two vectored valued functions, right? I can just find out the position of the center of this wheel, and then I'll add this to the position of the point relative to the center. And so ultimately, my final vectored valued function, I'm going to get r of t. That's going to be equal to, and I can factor out r from here, so r times omega t minus sine of omega t. And then this is going to be comma, and then r times 1 minus cosine of omega t. And then if we let theta be equal to omega t, then we can substitute thetas in for everywhere we see omega t, and you'll find out that we get the same r of theta function that we have before. Okay, but this is the exact same formula for the cycloid that we've seen before. But this time, we're modeling it relative to the center, but we still get the same answer. Now, the cycloid is one of those equations where if you try and find an explicit relationship between the x and the y value, you'll find that it's pretty much impossible. Like there are like really good approximations for it, but overall, it's impossible, which is why parametric equations are useful for modeling this. The final thing that I want to cover is when a cycloid is moving. So let's just simplify things, and let's say that the radius is 1. And also, by the way, if you had a negative radius, it would be traveling the opposite way. Just if you're curious about that. Let's say if the radius is equal to 1, and then you have this traveling. What do you think happens at the bottom of this? What happens at the bottom of this? Now, when do these cusps even occur in the first place? Well, notice how in order for the circle to make a single rotation, so like in order for the circle to make a single rotation, right? So you can think about the position of these cusps as when the circle makes a full rotation, right? In order for the circle to make a full rotation, well, you have to have traveled a circumference of the circle, right? This is just the circumference of the circle. And so 2 pi times the radius, which is 1, well, then that's just going to give me around like 6.2 something, 6.28, right? So that's where this cusp is, right over here. and then any multiple of 6.28. So you can see this occurs at somewhere around 12. This occurs at somewhere around 18. So you can see that multiples of it will also have the cusp, because you're essentially traveling a circumference every time, right? You're jumping over a circumference every time. So we can generalize this, and we can say that the cusps of a cycloid occur at 0, or sorry, we know that the y value has to be 0, right? Because it's at the bottom, and it's going to be 2 pi times the radius times any multiple of that. So 2 pi r times n, where n is an integer. Okay? Now, just to make our lives a little bit simpler, right, this isn't going to change the result. We're going to let r be equal to 1. So we're going to let the radius of our cycloid be equal to 1. And so this is just the simplified version of this formula. But still not going to change the overall shape of all of this. Like, you can see that when I set the radius equal to 1, when I set the radius equal to whatever value it is, you're still going to have the cusp. What's actually really nice about this cusp is that it's actually the point where rotational motion, it will cancel out with the forward motion. So we saw how in the previous proof, right, we broken down the motion of the cycloid into the movement of the center and then the movement of the point relative to the center, right? So basically the rotational motion. Well, at that specific cusp, right, so if we were to trace out like the graph of this, at that specific point where the circle reaches the cusp, notice how the rotational motion, right, we're kind of going backwards here, but that perfectly cancels out with the forward motion. So it creates these little peaks that are, or these little dips that are in the function. So let's think about the rate of changes of this. So I want to find dx over dt, or x prime of t, right? So I differentiate this, and I also want to find dy over dt. So let's model how this cycloid is moving over time at those specific cusp. So this is just going to be equal to dx over dt is just going to be equal to 1 minus cosine of theta. And then dy over dt is just going to be equal to sine of theta. And let's just pick, since our radius is 1, right, we know that the radius is 1, let's just pick n is equal to 1. So if we let n is equal to 1, well then we're just going to have the x value at 2 pi, or sorry, the t value at 2 pi. And sorry if I'm writing over dt. It should be dx over d theta, dy over d theta. So we're going to let the distance that we traveled be equal to 2 pi. So we're going to be at the first cusp. If I plug in 2 pi here, I'm going to get what? Cosine of 2 pi, that's going to be equal to 1. So 1 minus 1 is equal to 0. So dx over dt at theta is equal to 2 pi is going to be equal to 0. And then dy over dt at theta is equal to 2 pi. Well, what's sine of 2 pi? That's going to give us a y value of 0. So that's also going to be 0. So notice how at the instant that we are at the bottom, we're not traveling in the x direction, or our velocity vector is not traveling in the x direction, nor is it in the y direction. It's actually the 0 vector. And if I want to find out the rate of change of y with respect to x, remember the formula for that, right? That's dy over d theta divided by dx over d theta. dy over d theta divided by dx over d theta. And we see that we're just going to get 0 over 0. So in fact, the slope of this tangent line, so if we were to look at the relationship between x and y, you see that the slope of this tangent line is actually going to approach, it's actually going to not exist at all, right? Because we're going to get 0 over 0. So the slope of this is going to be, it's going to be extremely, extremely steep, right? It's going to approach negative infinity, actually, because we're going down, 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 and there we have it. In fact, we're done for velocity in this case, but let's actually think about acceleration. All right, so let's differentiate this once again. So we have 1 minus cosine of theta and sine of theta. If we differentiate this again, we get that essentially, I'm just going to write it as x double prime of theta, right? our x component differentiated twice is going to be equal to sine of theta. And then the y component differentiated twice with respect to theta, that's going to give me cosine of theta. And so if we find x of theta at theta is equal to 2 pi, and we do this for both, at theta is equal to 2 pi, well, what's sine of 2 pi? That's going to be equal to 0. And then what's cosine of 2 pi? That's going to be equal to 1. So it turns out that at these cusps, what's actually going to happen? Sorry, I'm just going to erase these pink lines. So at these cusps right over here, there's going to be a tangent vector that's pointing upwards. So the way to interpret the velocity being equal to 0, and at least for the individual components, right, the way to interpret the velocities being equal to 0 and then a tangent vector that's pointing straight up is that at these specific points, our position is like, it's temporarily at rest, right? It's not really moving in the x direction, nor is it moving in the y direction, but it's still being pulled up with a force upwards. So that explains why it's such like a sharp kind of turn, right? It's a sharp turn down and a sharp turn up. And so this acceleration vector pointing upwards, that matches up with this undefined slope that we got when we're finding out the relationship of y with respect to x.